Dear friends, welcome to my video. Kindly click on the CC button for subtitles. String theory is a proposed theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional objects known as strings. It is one of the most challenging and exciting areas of study within modern theoretical physics, primarily because it seeks to reconcile the seemingly incompatible realms of quantum mechanics and general relativity, promising a unified framework for all fundamental forces. In traditional particle physics, elementary particles like electrons and quarks are treated as zero-dimensional points. However, string theory suggests a radically different view. These particles are not point-like, but rather tiny, vibrating strands of energy, or strings. Each string's vibration mode corresponds to a different particle, with the vibrational state defining the particle's properties. For instance, an electron is not merely an electron but a string vibrating in the electron mode. String theory initially arose in the late 1960s and early 1970s as a theory of strong nuclear force, which binds quarks together inside protons and neutrons. However, the string framework was later found to incorporate gravity naturally, suggesting its potential as a theory of everything, a unified description of all fundamental forces. The concept of extra dimensions is another hallmark of string theory. Classical physics and special relativity posit a four-dimensional universe, three of space and one of time. However, string theory proposes that there are actually many more dimensions, most of which are compactified or hidden from our perception. In the simplest string theory models, there are 9 dimensions of space and 1 of time, but there are variants with up to 26 dimensions. Importantly, string theory includes a particular string whose vibrational patterns correspond to a graviton, a theoretical particle that mediates the force of gravity. This is a significant accomplishment because gravity has resisted all attempts to be incorporated into the quantum realm. That's the key advantage of string theory: it's a potential path towards quantum gravity. Moreover, string theory has led to substantial advancements in mathematics and has triggered the development of a new mathematical framework, string geometry. It has also provided new insights into black holes, conforming to the expectations from quantum mechanics, and potentially solving the so-called information paradox. However, it's essential to underscore that string theory remains unconfirmed. As of my knowledge cutoff in September 2021, no direct experimental evidence for string theory has been observed. Part of the problem lies in the energy scales at which stringy effects become apparent. The size of a string is presumed to be on the order of the Planck length, around 10 to the power of minus 35 meters, which is many orders of magnitude smaller than we can probe with current technology. Moreover, string theory suffers from a landscape problem, the existence of a vast number of possible false vacuums, each corresponding to a different universe with different physical laws. The anthropic principle, which suggests our universe is the way it is because we wouldn't exist in a universe with different laws, is often invoked to tackle this. However, this is a controversial stance among physicists. In conclusion, string theory is a vibrant, developing discipline that strives to marry quantum mechanics and general relativity. It has revolutionized our understanding of the microscopic world, provided new mathematical tools, and offered tantalizing glimpses of a unified theory of physical reality. However, its definitive verification remains one of the great challenges for future generations of physicists. Thank you for watching my video. Kindly subscribe to my YouTube channel and give a thumbs up. Thanks for your support.